let's do a completely different kind of data science, and something not to do with text at all. If you look at this page here, you might see what I see: fraud. It's completely wrong, all right? And here's why. You hover over this video, well, it doesn't do anything, but this is not the entirety of the video. This is only one moment in the video. How can you possibly claim that this represents what the video will be? It's the YouTube disappointing thumbnail problem, and we can solve it with data and a couple of command line tools. So what I want to write is an accurate thumbnailer for YouTube videos. You take a YouTube video URL, you run some script on it, and then it emits an image, which is the composite average of every single frame in the entire video. And it's actually really easy to do this if you have a couple of tools which we can easily get. So there are two tools that we need. One is called YouTube DL. YouTube DL, which is available from here. You could install this also with the Ubuntu Package Manager, but it'll be out of date. And YouTube DL is very sensitive to being up to date because YouTube will try to prevent it from working, or at least they change frequently enough that it breaks a lot. So if you have a tool like that, you install it from their thing, and then it has an auto update. As it happens, I've already downloaded a video with it, so we won't need to do the install again. And then the other tool is ffmpeg. So let me pull that up and show you what that does. It gives you, well, not a very helpful thing, as is kind of what you'd expect for a Linux tool, but that's okay, because I'll explain a little bit about how this works. So first off, I downloaded one of my videos, Linux Data Science. The reason I use my own videos is because I'm not going to sue myself for downloading them. So Linux Data Science Part 1, and I can ffmpeg that. And before I go any further, let me talk a little bit about what ffmpeg does. It's a general purpose conversion tool from media formats to media formats. It's really awesome. And it knows basically every video and audio codec. And it also knows some image codecs and other like useful things that let you do things like for a case like this. You can take the video and you can export every single frame as a separate image file. I don't really want to do that because it'll use up a lot of space, but what we will do instead is we can say this. fimage2pipe. I guess I should explain a little bit about what this, what the format of this command line is. So the first thing you do is you specify modifiers for the input. So any filter modifiers, like how to interpret it. -f is format, so you might specify that. And then you say -i for the input file. You can have multiple inputs and it kind of keeps track of them and lets you do stream mapping and stuff. I won't get into that though. And then starting here, we have modifiers for the output because we're starting a new group of modifiers, but we haven't said what it is for yet. So we're talking about the container format here, -f. And I'll talk a little bit more about this later, but for now, let me just set this up. ppm dash. And I think that will give us a series of ppm images. Yeah, here we go. And so if you don't know, ppm is a fairly generic image format, and p6 means color binary, 3-channel, I think it's 3-channel RGB. This is the resolution, and then this is the maximum pixel value. And then from here, it's just bytes. It's RGB, RGB. I think it's RGB. It might, that should be RGB actually, because this up here is blue, and that looks like no red, some green, some blue. So that is probably RGB. It won't matter for us because we're just going to treat it like bytes. Anyway, so it's a series of these things, and they're just like concatenated one after another. So if we want to average them all together, it's actually pretty simple to do that. All we have to do is grab the pixel data into a big buffer of memory and then sum it, pixel by pixel, or rather color component, into this aggregation, keep track of the number of frames we've seen, and then finally at the end we do a division and then we output a new buffer. We can do this with C pretty easily. So since we're going to be using C, we need to install a C compiler. And in Ubuntu, there are a couple of ways you can do it. You can install GCC, but that's a little bit lower level than what we probably want, which is Build Essential. Build Essential includes a bunch of stuff that's kind of useful for building C programs, or programs in general. So it's good to have kind of the whole suite of things. All right, so while that's going, let's start writing our program. Actually, let's design it a little bit first. What I want to make sure of is that we're not going to have a memory buffer that's just unreasonably large. And a program to help us with that would be a unit calculator called units. I already have it installed, but if you don't, this is how you would install it. So let's do a quick, some quick math to make sure that we're not going to allocate tons and tons of memory. It was a 4K resolution, so 3840 times 2160. And let's say we're going to aggregate into 32-bit integers, so 32-bit. And then we want to know how many megabytes that'll be. 33 megabytes. Oh wait, but there's 3 color channels. So we want, okay, so it'll be 99 megabytes, which is okay, we can work with that. All right, that sounds fine. So now let's write some code. I'm just going to write this in low-level C. There are 2 kind of ways you can do I/O in Linux. We need some man pages for C development. This is really useful to have. I recommend you install this if you're going to do this stuff. So you do apt install man pages dev. We might get that automatically. Yeah, we do. Okay, so Build Essential gave that to us, which is really nice. We can say things like man2 read, which is just like the kernel level. It's not strictly kernel level, but it's basically the same. It's below most of libc. So kernel level interface to reading data into buffers and stuff, and so just kind of a useful thing. It tells you which include files you need, which is always good. All right, so unistandard.h is like standard Linux utilities, I guess, or Unix fundamentals, usually POSIX functions. Okay, so what are we going to do here? Should like talk less and code more. Okay, so we'll have some static data out here. I'm going to import standard int because we'll want like standard sized int types. I'm just more comfortable using those. So we'll say like unsigned int 32s, and this will be the aggregation, so totals, and then 3840 times 2160 times 3. I think we can initialize it like that. We might have to use C99. We'll see. Okay, and then this is pretty simple because all we have to do is, I think, read will give us 0 on EOF, as I recall. If the file offset is at or past the end of the file, no bytes are read. Yeah, read returns 0. Okay, so this is pretty simple. We just say, we'll say int EOF equals 0, and then, while not EOF, we're going to read a frame, and we're going to have a single frame buffer, which is going to be the length of the header plus the number of bytes we expect to read. So let's do some quick math on that. If I recall right, the header was P6, 3840 space 2160, and then 255N. So that is prepended to everything, and we can ask Perl for the length of that. Print length of this. So we can't select it, can we? We can. Unix or Linux has a nice thing where you can 17. Okay, you can select text and then middle click to paste it, and it's really handy. When you get used to it, you don't really want to use copy and paste keystrokes anymore. Okay, so we're going to need an unsigned char buff, uint8t buff, it's fine, 3840 times 2160 times 3 plus 17. And I'm going to put that in a constant. That's pretty awkward. So define frame size. By the way, I'm not taking any care to write good C. Like this is not at all a way I would recommend to write C code in general. but it'll do for this because this is basically throwaway code. All right, so we want to read data into this, but we might not get the whole thing in one request. So what we're going to do is we're going to keep going until we've read enough stuff. So we'll just use a for. Yeah, for int red equals 0, int r equals 0. R is less than frame size. And nothing yet, because we will just increment here. So we'll say r plus equals, oh, we gotta store the EOF stuff too. So int n equals read. 0 is standard input, so we'll just do that. Buff plus r, and then frame size minus r. All right, if not n, then we are done. And actually, this is the point to observe it anyway. We could just say exit 0. I think it's underscore. It might be underscore exit. Yeah, it's underscore exit for whatever reason. That's fine though. R plus equals n. Okay, that should do it. So now we have a buffer of stuff, and I'm gonna factor off the header length to header size 17, and then we'll just say header size. Okay, so at this point, we're going to say for int I, you know what? We don't need these to be ints, we want these to be longs, just to be on the safe side. Long I equals header size. No, we'll add, so equals 0, I is less than, here. Data size. These are not very good names, but that's okay. Okay, so data size plus I. All we're doing is summing up each component into the totals. So totals I plus equals buff header size plus I. And oh, and we're going to increment the number of frames too. So equals 0. We don't need EOF anymore. So while true. And we're going to say plus frames. And of course we don't exit 0. That's not what we do at all. Silly me. What do? We break out of the outer while loop. So outer and then break outer. That's what we want to do. Okay, anyway. And that's basically it. So now we divide each entry in totals by the number of frames. So long I equals 0. I is less than data size. Okay, and the very last thing we do is we print the same header out. So we can use write to do this, and that way we don't have to do any like printf or anything. So write to standard output, so which is file descriptor 1. Oh, but if we, okay. Well, we know it's 17 bytes. This is kind of a hack. What about this isn't a hack? 2160, and then 255. Like, don't do this way, I would say. The totals won't work because it's a bunch of 32-bit numbers. So what we need is to convert that into a regular buffer. And actually, oh wait, what am I doing? This would be way better. Okay. Rather than doing this, let's just say buff header size plus I equals totals I over frames. And we'll have to convert that. Even 8t of that. That's better because that way we'll just carry whatever frame header we had from before. So that should be fine. And then we can just write buff. One buff, and then I think it's just frame size. And that's it. Return 0. I don't think this is going to work, but let's give it a shot. To test this, let's go ahead and create a stream of like a handful of frames. A way to do this would be ffmpeg -i Linux data science. Here I think it's -st. I always forget this option. ffmpeg, it's like time you want to extract, and I think it's either -t or to or something. Extract first 10 seconds, yeah. -t. Yep, encoding duration, which is fine. So let's extract, I don't know, 0.02.00, so 2 seconds worth. Should be about 30 frames, I think. And let's just write these out to a file. So images. Cool, okay. Plus images, yeah, that looks good. So now, geez, I'm gonna use C99. Oh. Am I doing this completely wrong? I might be doing this totally wrong. Break outer. You can break to a label, can't you? Maybe not. Okay, let's do this even worse. Let's just put a label here and use goto. Goto always works. When in doubt, use goto. Don't use goto, that's terrible advice. Okay, images. Oh, segmentation fault. That's terrible. All right, time for GDB. Oh, no, that's not right. GDB is capturing the input. We don't want that. Oh, no, stop. All right, let's kill it. Okay. I completely screwed that up. You don't use GDB this way. You do this and then say run less than images. Okay, backtrace. Yeah, okay. That's really not helpful. Let's compile with debug information. You can say C99-G. Okay. Long frames equals 0. That's interesting. I wonder, oh, I bet it's that we've just stack allocated something giant. Yeah, we can't make this a local variable, it's too big. That makes sense. Okay, we'll just put it up here. So that'll be static data as well. Oh, you know what, let's move these down here. So totals, data size, clean this up. And that's frame size. Okay. Once again, we are not going to win any beauty contest awards, but that's okay. All right, let's try that. Cool. We should have like, oh, sweet. That looks like it might be something. Okay. All right, and it corrupted our terminal. If this ever happens to you, just run reset, which I just typed, but you didn't see it that way. Okay. We're going to need one more program to display ppm images. So let's do this real quick. A.out less than images into output.ppm. And let's install another program. I like to use a program called ffmpeg because it's just very minimal. You can use a lot of image programs, but this is nice because it'll take input from standard in. And so we can say ffmpeg output.ppm. And I want to see if this gives us anything resembling an averaged image or if it's a bunch of garbage. That actually kind of looks average to me. I think we totally did this. All right, I'm going to improve my program just a little bit by adding a print to standard error. And you know what? I'm just going to bite the bullet and use standard IO. Life's too short to do printf by hand. Okay, so all we have to do here is put a frame count. It's fprintf. Standard error, I think it's fprintf. I'm kind of rusty on this. I've been doing very different things lately. I haven't used C in a while. I feel bad about that. Like I always feel bad if I'm not up on C because it's a great language. Sure, that should do it. And then just to be safe, fflush standard error, because we want this stuff to come out onto the terminal really quickly. Oh, there's a trick actually that you can do, and I think it's worth doing here. You can use R, \R. This is carriage return. It'll send the edit point back to the beginning of the line without going down, and so it allows you to revise the line by just creating new text and overwriting it. And you'll see like PV did this when we were like showing file progress. It was just going back to the beginning of the line and then printing a new status. And that's why I didn't just you didn't fill up the terminal with status updates. Anyway, it's kind of a nice thing to do. I'm just going to make sure fflush, yeah, okay. We shouldn't need fflush here. I mean, it shouldn't be bad, but I'm just going to do it anyway. Cool, and then we'll just, for completeness, standard error, new line. That way we'll end with a new line so that whoever comes after us isn't going to be stuck out on the end. So let's aggregate all of Linux data science. And the way to do that would be to take our ffmpeg command, and instead of piping into images, I'm going to silence ffmpeg by saying to dev null. 2 is standard error. So what that's going to do is just send all the diagnostics that usually prints out into the dev null device, which goes nowhere. Oh, I forgot to recompile, didn't I? And we'll use some optimization too. We should really do that. So oops. No. C99-02. And we don't need debugging anymore. We can just do this. Oh, right. Yep. And I don't really care about warnings. But I do care about this. I forgot about that. L means long end. Okay, warning, that's fine. So I think this will do what we want. Hey, look at that. Oh, this is cool. Oh, right, because we only did 2 seconds worth. Let's do all of it. I don't know how many frames there were, but I'm guessing it's a lot. And I'm not going to have you guys wait for this to finish. So I'm going to cut the video here and then report back. All right, it is finished. That didn't take that long. Here is what it looks like. A 100% objectively accurate thumbnail. This is the average. That's kind of disappointing. It looks a little boring this way. I don't know. I think there's potential though. Anyway, let's. The reason I call this data science, it isn't really data science anymore, right? We're just doing image stuff, but it kind of is related to data science because you have to be very conscious about space usage. And if I were to do this, let's count up the number of bytes we would get from this if we didn't, like, just if we streamed all the images out. Probably a lot, but let's find out. I'm going to use PV for this, so we can monitor. But I mean, you can see the numbers here, right? This is a non-trivial amount of data. Certainly couldn't hold it in memory, and you probably wouldn't want to hold it on disk. 4K frames. Well, we did the math earlier. They they were 25 megabytes each, give or take, and 15 per second times however long the video was, which was 10 minutes or so. 600 seconds. So, I mean, it's a big number, right? Yeah, many gigabytes. And the thing to note here is that our program used 100 megabytes of memory constantly and then just wrote one image out. And that's a, like, that's a useful enough kind of thing that you do it all the time when you're doing big data stuff. I mean, in a way, movies are big data. They're so highly compressed, you have to treat them that way. So anyway, it's just worth mentioning, like, this is not strictly data science in the usual way, but if you think this way, you're going to have a big advantage when you're doing data science in the field, because you're just not going to run out of memory nearly as often as if you're sort of oblivious to it. Yeah, 25 gigs and counting. All right, this video is long enough. I think we've gone off on this segue pretty well. But yeah, just a fun, quick project that isn't about text or traditional data. So I will see you guys next time, I think, with more OpenStreetMap stuff, if I can stay on focus.